And it's single speed from 0 to 200 miles an hour. So it's just, the RPM is so crazy that just the centrifugal force wants to expand the rotor. So the carbon overwrap actually holds the rotor, basically holds the rotor together. It's like madness.
At its investor day, Tesla handed its engineering team a target that sounded almost too simple: create a motor that is cheap enough to slip into millions of cars. What they built was so groundbreaking, it broke the one cardinal rule the automotive industry had always followed, a trade-off that no one thought could be bypassed. The new motor was way faster than machines 10 times its price. It ran far more efficiently than any of its competitors, and its design was so hard to replicate that rivals will need decades to catch up.
We're going to show you the motor. In fact, you might have had a chance to see the drive unit. I mean, this is really an amazing work of engineering.
This new engine was never supposed to be this powerful. But then how did Tesla manage to build it? And why is it making every rival company fear for their future? The company nobody feared. To understand why one motor could make automotive giants stop dead in their tracks, we need to first go back to a time in Tesla's story that almost no one remembers anymore. Because it's important to remember that for years, no one thought Tesla could build something like this. The stage was dominated by the biggest automakers in the world for decades, all fighting to determine who would change the industry's future forever. When electric vehicles were first introduced to the world, they weren't just a new type of car. They were a force that changed the very direction in which the global auto industry was headed. Early on, at the very forefront of the electric revolution, was none other than Tesla. But at the time, no one really thought that it would stay in that spot. The company was ambitious, daring, and innovative, but at the same time, it was new and inexperienced. Compared to industry giants like Ford, General Motors, Toyota, and Volkswagen that completely dominated the market, Tesla was barely an infant, a fragile dream that could be shattered by one swing of the automotive industry. The established names already had numerous factories, established supply chains, and heavily engineered production infrastructure in place, built over generations. Tesla had none of that. Common sense and market knowledge dictated that the new guy would be out the door soon enough once the established names caught up. And sure enough, it seemed that's exactly what was going to happen. Tesla's competitors quickly began improving. Their cars started to become more advanced with better efficiency, reliability, and battery performance. The writing on the wall was clear. The rivals were catching up. Soon enough, analysts were forecasting what they thought was inevitable: that Tesla's time in the limelight was over, and the giants that ruled the automotive industry were here to replace it. But at this critical point, Tesla did the impossible. It flipped the script and made a breakthrough that changed the industry's power dynamics forever. Their new invention wasn't some body change or software update. It was a new innovation at the very heart of every EV: the engine. When rival companies tore down the engine to find out what was different, they all felt uneasy upon seeing the secret. Like the veteran teardown engineer Sandy Munro, who opened a Model S Plaid drive unit. Immediately, his eyes were transfixed on one thing wrapped around the spinning core. The invention he saw there was astounding. He knew then and there that Tesla had exceeded a threshold that none of its rivals could hope to reach anytime soon. It was now in a league of its own. With this innovation, Tesla's engines didn't just have power and efficiency far exceeding other EV brands. They also had a system that no one could replicate. Analysts predicted it would be decades before anyone else builds something even remotely as effective. And by the time that happens, Tesla would already have made another big technological leap forward. But as it turns out, the invention was only half the genius. The other half of it was choosing the right moment to reveal it. So how do you decide the right time to reveal something so revolutionary? The answer lies with a truck that pretty much no one wanted to buy. The truck that forced Tesla's hand. Tesla needed another engineering win at a moment when its boldest vehicle was struggling to become the success Musk had imagined. Cybertruck had arrived with huge expectations. Musk had talked about eventually producing roughly 250,000 trucks a year, depending on demand. During its first full calendar year on sale, Cox Automotive estimated almost 39,000 US sales. In 2025, that figure fell to just over 20,000. By the first quarter of 2026, US sales had dropped to about 3,500. The registration data made the picture even stranger. During the final quarter of 2025, SpaceX registered 1,279 Cybertrucks in the United States. Musk's other companies added another 60, bringing their combined share to almost 1/5 of all Cybertruck registrations that quarter. Cybertruck was meant to show that Tesla could reinvent the pickup the same way it had helped reshape the electric car. Its slowing sales instead put more pressure on the company to prove that its engineering advantage still reached deeper than one polarizing vehicle. At the same time, Tesla was preparing its largest investment cycle yet. Its 2026 capital spending plan climbed above $25 billion, almost 3 times what the company spent the year before, with much of that money flowing into manufacturing, artificial intelligence, and other future technologies. That appetite for expensive engineering experiments runs through the Cybertruck itself. Tesla says its engineers developed a new stainless steel alloy called HFS after conventional automotive materials failed to meet the durability targets they had set for the truck. The solution came from changing the material rather than designing around its limits. The same philosophy had already appeared somewhere far less visible. Inside Tesla's Plaid drive unit, engineers had taken one of the hardest limits in electric motor design and attacked the material holding the rotor together. Carbon fiber allowed that rotor to survive enormous forces while spinning at around 20,000 revolutions per minute. Cybertruck had shown how risky Tesla's biggest engineering bets could become. The motor showed what happened when one worked. The rule this engine broke. For years, electric performance came with an expensive compromise. More power placed greater stress on the motor and produced more heat, while the hardware needed to handle it added weight. Efficiency pushed engineers in the opposite direction, toward lighter systems built to stretch every charge. Tesla attacked that compromise inside the drive unit. The answer was a rotor wrapped in carbon fiber. Inside an electric motor, the rotor spins inside a stationary ring called the stator. In Tesla's Plaid design, permanent magnets sit around a laminated steel core. As the rotor spins faster, centrifugal force pulls those outer components away from the center with increasing force. High-speed permanent magnet motors need a way to hold that assembly together. Tesla replaced more of the metal normally used around the magnetic structure with a tightly wound fiber sleeve. Its patent describes carbon fiber wrapped around the rotor under high tension, holding the magnetic pieces in position while the motor spins. Carbon fiber offers exceptional strength for its weight, giving the rotor the support required for much higher speeds without surrounding the magnets with as much metal. That second part matters because metal around the magnets can steal some of the magnetic flux the motor is trying to use. Tesla's patent describes a design with fewer metal connections around the magnetic pieces, allowing more of the field to reach the stator. The company says this can improve torque and high-speed power from the same basic motor envelope. The difficult part was manufacturing it. Carbon fiber works best when the strands carry tension along their length. Tesla, therefore, had to wind the sleeve around the finished rotor while pulling the fiber extremely tight. Its patent describes a special tensioning system that feeds the material around the rotor while limiting damage to the fibers. The process creates a thin shell, already squeezing inward before the motor ever begins to spin. Once the rotor accelerates, that inward pressure works against the enormous force trying to pull it apart. The Plaid motor could spin at roughly 20,000 revolutions per minute, giving Tesla another way to make enormous power from a relatively compact drive unit. And compactness is where the real advantage starts to appear. Electric traction motors were already remarkably efficient, so the breakthrough was never about discovering a huge reservoir of wasted battery energy. Higher rotor speed allows engineers to pull more power from a smaller motor. A smaller motor can reduce the amount of material packed into the drive unit while leaving engineers more freedom elsewhere in the vehicle. The carbon sleeve also lets Tesla expose more of the magnets to the useful magnetic field because the wrap interferes with that field far less than additional iron around the rotor would. Tesla's patent says the wrap design can generate more torque at the same speed and improve high-speed power by reducing magnetic leakage. Plaid turned those engineering gains into something anyone could understand. 3 carbon sleeve motors produced 1,020 horsepower. Tesla rated the car at 0 to 60 miles per hour in 1.99 seconds, while the same four-door sedan still offered hundreds of miles of estimated driving range. Tesla also paired those motors with an upgraded battery and thermal system so the car could repeat hard acceleration with more consistent power. That combination made Plaid remarkable. The motor delivered extreme power without turning the rest of the vehicle into a dedicated track machine. By the second quarter of 2026, that chapter had closed. Tesla decommissioned the Model S and Model X production lines at Fremont as the company began converting the space for its first large-scale Optimus factory. The engineering problem Tesla solved inside Plaid remains more interesting than the car's production run. Anyone can understand the basic idea after seeing the rotor. Building it repeatedly is much harder. The carbon fiber has to circle the rotor under controlled tension while staying evenly placed across its surface. Tesla's own manufacturing patent describes a winding system that rotates the rotor while feeding tensioned fiber through a resin process, building the sleeve layer by layer to a controlled thickness. At 20,000 revolutions per minute, tiny manufacturing errors become much larger forces. An uneven rotor creates vibration, and the faster it spins, the harder that vibration becomes to control. Every finished assembly therefore depends on precise winding and careful balancing before it reaches a car. That is what makes the technology difficult to reproduce at scale. Understanding a carbon sleeve takes minutes. Building a production process that applies it consistently takes tooling and manufacturing experience. Tesla spent those years learning the process through Plaid. And once a motor can spin that fast inside a road car, another question becomes far more important to the person buying it. How well does all of this hold up after years of everyday use? The engine that outlives the car. The performance story gets even more useful once the car leaves the test track. A gasoline engine creates power through thousands of controlled combustions every minute. Pistons move through cylinders while valves open and close above them. Oil keeps those surfaces separated, and a cooling system carries away the heat created along the way. An electric drive unit has a much simpler job. Electricity creates a magnetic field in the stator. The rotor spins, and a fixed reduction gear sends that motion toward the wheels. Fewer wear-heavy systems also mean fewer scheduled jobs built into the ownership cycle. The energy difference is just as striking. The U.S. Department of Energy estimates that a typical electric vehicle sends about 65 to 69% of the energy stored on board directly to the wheels. Regenerative braking recovers another portion during slowing, bringing overall efficiency to roughly 87 to 91% on the combined driving cycle. A conventional gasoline vehicle reaches about 30%. That gap comes from the way each powertrain creates motion. A gasoline engine loses much of its fuel energy through heat and other engine losses before the wheels ever receive it. An electric motor converts energy into motion far more directly. The same simplicity shows up in Tesla's service schedule. Tesla vehicles skip the regular oil changes and exhaust system work that come with combustion engines. Tesla's current maintenance guidance centers much more heavily on tires and filters, with brake fluid testing every 4 years and other service depending on the model and driving conditions. Tire rotation is recommended around every 6,250 miles. Regenerative braking helps here too. During normal slowing, the electric motor works as a generator and sends energy back toward the battery. That reduces how often the friction brakes have to turn the car's motion into heat. Tesla says its brake pads are typically used less often than those in conventional braking systems. The drive unit also carries substantial factory coverage. Tesla currently warranties the battery and drive unit in Model S, Model X, and Cybertruck for 8 years, or 150,000 miles. Model 3 and Model Y coverage runs for 8 years, with mileage limits that depend on the version. That warranty gives us a firmer measure than the million-mile lifespan figures often repeated online. Tesla has published ambitious durability goals over the years, while its current warranty sets the period the company actually promises to stand behind the drive unit. The financial advantage becomes clearer across a vehicle's life. Consumer Reports analyzed maintenance and repair spending from hundreds of thousands of members and found that battery electric vehicle owners spent about half as much as gasoline vehicle owners. Its study estimated roughly $4,600 in lifetime maintenance and repair savings for an EV owner. That figure covers the whole vehicle rather than proving that every electric motor will last a certain number of miles. Tires still wear, suspension parts still age, electronics and other components can still create expensive repairs. The drive unit simply removes a large collection of routine mechanical demands from the equation. And that gives the carbon sleeve motor a second kind of appeal. Plaid proved that an electric drive unit could deliver extraordinary performance from a compact package. The broader electric architecture lets that performance live inside a car with a remarkably light routine service schedule. The acceleration makes the headline. The ownership experience is what stays with you after the launch. Why the copy never arrives. A prototype proves an idea works. A factory has to prove it again thousands of times at the right price. Tesla learned the difference during the Model 3 ramp when the company pushed automation so aggressively that Musk later called the excess a mistake and said humans were underrated. Those painful years changed the way Tesla approached new products, turning manufacturing into part of the engineering problem from the beginning. That philosophy appeared clearly at Tesla's 2023 Investor Day, where powertrain chief Colin Campbell presented a next-generation drive unit designed to cost about $1,000 for the motor, power electronics, and gearbox together. Tesla also targeted 75% less silicon carbide and a permanent magnet motor using 0 rare earth elements. The rare earth target became much more important 2 years later. In April 2025, China introduced export controls covering several heavy rare earth elements and related magnets, tightening a supply chain already concentrated heavily inside the country. Some automakers and suppliers were forced to slow or interrupt production as magnet inventories tightened. Electric drive motors are only part of that exposure. Rare earth magnets appear throughout modern vehicles in smaller electrical systems, which means a disruption can reach several parts of a factory at once. Tesla's proposed motor attacks that dependency at the design level. A permanent magnet machine built from more widely available materials could give the company greater control over supply and cost, although Tesla has yet to reveal the magnet material or put the design into volume production. Silicon carbide follows the same logic. These power semiconductors help the inverter move electricity efficiently between the battery and motor, so reducing the amount required could cut another expensive component from the drive unit. That matters because making good electric cars has become only half the challenge. Making them profitably is where the pressure now sits. Ford's electric operation lost billions during 2025, while the company reshaped its EV strategy around cheaper future models. Rivian continues preparing the smaller R2 while carrying heavy losses of its own. BYD has reached genuine scale through deep battery integration and lower-cost vehicles, giving Tesla a rival that can compete on volume as well as manufacturing. Tesla's answer is to push the drive unit itself toward lower material use and cheaper production. The carbon-sleeved Plaid motor showed what the company could do when performance was the target. The next-generation unit shifts that same attention toward manufacturability. A competitor can study the finished hardware. The harder advantage sits in the process that produces it. The machine behind the machine. Tesla's drive unit sits inside a much larger manufacturing system, and the battery program shows how that system works. The company introduced its 4680 cell with an ambitious goal: simplify battery production while bringing more of the process under its own control. Scaling it took years, but by early 2026, Tesla said its Texas operation was producing 4680 cells, with dry electrode processing on both the anode and cathode, and some of those cells were moving into Model Y packs. Dry electrode manufacturing matters because it removes several energy-intensive stages used in conventional wet coating, potentially shrinking factory space and production cost. Once the process works reliably at volume, Tesla gains another kind of flexibility from controlling more of the software around its hardware. During the global chip shortage, the company substituted alternative components and rewrote firmware so those chips could work inside existing vehicles, allowing engineers to treat a supply problem as a software and electrical engineering problem, rather than simply waiting for the original part. Charging extends that system beyond the factory. Tesla's supercharger network has grown to tens of thousands of connectors worldwide, and many competing automakers now give their drivers access to compatible Tesla stations across North America. That means Tesla can still earn charging revenue when another company sells the vehicle. the advantage is less absolute than it once was, because rival charging networks are improving quickly, and several now score extremely well for customer satisfaction. What Tesla built earlier was a connected set of capabilities. Vehicle engineering tied to battery production, software tied closely to the electrical architecture, and charging infrastructure large enough to serve drivers from other brands. Each piece has serious competitors. The difficult lies in making those pieces work together quickly enough that an improvement in one part of the company can strengthen another. The game nobody else signed up for. Tesla's next contest is moving beyond the motor entirely, because every vehicle can also become a source of driving data. Cameras and onboard systems capture examples of real roads, changing weather, unusual traffic behavior, and the difficult situations autonomous driving software has to learn to handle. For years, Dojo was meant to process much of that information through Tesla's own training hardware. That strategy changed in 2025 when the company dissolved the Dojo team and shifted more attention toward newer AI chip families that could serve a broader range of training and inference tasks. The computing effort itself continued. By the first half of 2026, Tesla had expanded its on-site AI capacity in Texas through the Cortex infrastructure used for autonomy work across vehicles and humanoid robots. The company is also working toward greater control over future semiconductor supply, including new chip-related infrastructure in Austin. That puts the carbon-sleeved rotor from the beginning of this story into perspective. Tesla keeps applying the same basic instinct to different bottlenecks. Plaid attacked the mechanical stress of a rotor spinning at extreme speed. The next drive unit targets material use and production cost. Autonomy pushes the problem toward data and computing power. Each challenge needs a different solution, yet the advantage comes from how quickly those solutions move into products. That is also why the EV race has become harder to score. BYD has already passed Tesla in annual battery electric sales volume. Ford is rebuilding around a lower-cost EV platform. Charging networks are closing the convenience gap. Rivian and Lucid continue developing strong electric architectures of their own. Tesla's challenge is to keep connecting its strengths faster than those rivals can close individual gaps. The carbon sleeve motor became interesting because anyone could open one on a bench and see what Tesla had built. The harder part to photograph is everything behind it. The tooling that makes the rotor, the battery lines coming online in Texas, the software that adapts around new hardware, the charging network spread across highways, and the computing infrastructure training the next generation of vehicles. The motor can be studied. The system behind it takes much longer to reproduce. And that is why the electric vehicle war is still wide open.